today. So our problem is the modeling of a pumping swing through ordinary differential equations. After exploring different types of modeling, such as the shortening and lengthening of the pendulum and the changing of the center of mass with relation to the pendulum, we decided to actually model the pumping as an outside force periodically acting on the swing whenever it reaches the apex of its motion. So this periodic pushing force would be much like a parent pushing a child on a swing, and it acts in frequency with the swing so that they resonate with each other ideally. Um, and this later on in our presentation, you'll be able to see this outside force being represented by our forcing function. So also, as you will see later, we use three different types of equations to model this motion. The first being the sine equation, which is our most accurate model, as it represents the greatest number of theta values. And then the Taylor polynomial approximation of sine will be next. And then finally, our small angle approximation of sine, which is just theta. And this is our most inaccurate model because it only represents about a theta change of about 5 or so degrees on either side. So also to further simplify our equation, we decided to do away with all outside forces except for gravity. As you can see, the force of tension, and then also the pushing force from the parent. And then we also decided, as you can see, to model the child as just a simple crowd mass, so that way its moment of inertia would not come into play when deriving our ODE model and modeling it in math lab.
So if we look at the forces that are acting on the pendulum, we have a force of gravity pointing downwards, and the force of tension in the direction of the string. And just for reference, this is where theta would be. So the magnitude of force tension has to equal the magnitude of gravity cosine theta, which is this component right here. Otherwise, we would no longer have a pendulum. The force that's causing the pendulum to move at an unconstant velocity is the sine component, which I'm going to rewrite as mg sine theta. So since this force is the only force that's causing the pendulum to move, we can use Newton's second law and set that equal to mass times the acceleration, which we derived here. And if we set up as positive and down as negative, the acceleration would have to be negative. And this is what we would have if we assume that there was no friction in the system. So if I cancel out mass and rearrange this equation a little bit, we would have d squared theta over dt squared plus g over L sine theta equal to 0. And this would be the simple model of a pendulum. As you can see that there is no mass in this equation because the mass of a pendulum does not affect the motion of a pendulum. For modeling using an outside object exerting a force, we will need a forcing function. So for our ODE, we set the length equal to 3 meters, gravity equal to 9.8 meters per second squared, and the forcing function cosine 2t. So the most basic ODE looks like this, where we keep the sine theta in and everything's as is. Next, we decided to use two approximations of sine theta. The first one is a Taylor approximation of sine theta, which is right here. And then our final sine approximation, we decided to use a small angle approximation, which comes from the Taylor approximation. And this function was the one that showed the resonance in our graphs.
Our first step was to model the simple pendulum. There is no damping or forcing function acting on this pendulum. It is simply swinging back and forth. In our initial attempts to showcase resonance in the swing, we modeled the point mass moving up and down as the swing moved back and forth. Essentially, the movement of the center of mass of the point mass was changing the length of the swing periodically. This is what pumping is. We tried this with different changes in the length of the swing. However, it was not successful as we could not determine how to showcase resonance. Our next step was to consider the equation for the movement of the pendulum. To get resonance, we used the small angle approximation for sine theta. This made concluding the natural frequency of the swing much simpler, as the equation is just the square root of k over m. Using this, we obtained a graph that clearly displayed resonance. However, this is not realistic, as this approximation is only valid for small angles of theta. It was suggested to us then to consider the next few terms of the Taylor series for sine theta. When we substituted theta minus theta cubed over 6 plus theta to the 5th over 120 in for theta, it became clear that our equation with the small angle approximation is not very accurate. The more realistic swing with these initial parameters, such as a length of 3 meters and a forcing function of cosine 2t, showcases beats rather than resonance. Beats is what occurs when the frequency of the forcing function and that of the swing are not the same. Although more accurate, this equation, like that of sine theta, makes it difficult to calculate the natural frequency of the swing. The equation square root of k over m is not applicable. Hence, resonance is difficult to achieve. To see just how accurate this Taylor approximation for sine theta was, we decided to graph the differential equation with sine theta included. As you may have noticed, they look identical. This is because the approximation of sine theta with 3 terms is valid for a larger range of theta values than the approximation with only 1 term. Overall, while our simple model with just theta is only valid for small values, our complex model with sine of theta is applicable to a greater range of theta values. We initially were unable to get reasonable graphs when using sine theta. After much trial and error and finagling with MATLAB code, we were able to arrive at an ODE which represents a reasonable model for the swing. Although we have yet to discover how to understand the swing's natural frequency from this equation, with this ODE, a swing's movement can be revealed. In the end, we decided to keep the advanced model as our final and most realistic ODE.
Hey everyone, it's Meena again. I'm just wrapping up our project here, explaining to you guys what we would do if we had more time to extend on our research and experimentation. So the first thing we would do would make sure that our forcing function actually resonated completely with our equations. So that would mean that we, instead of just having beats, we would have actual resonance, so that the amplitude of the swing would increase over time. And then we would also add damping, so that means air resistance and friction, and that would keep our equation to a finite amplitude instead of just increasing to infinity over time. So lastly, we would consider different types of pumping, so possibly from the seated position, standing up and down on the swing, leaning back and forth on the swing, just everything a kid would do in the playground.